After studying this module, you shall be able to know what are the charge transfer transitions. You will also learn about the origin of charge transfer transitions. You will identify the difference between LMCT and MLCT type of transitions. You can also analyze the complexes that show the charge transfer transitions. Now, introduction. First of all, we should understand what are the charge transfer bands. In case of transition metal complexes with octahedral geometry, the most important type of electronic transition involved is the DD transition, where the transition of an electron takes place from the lower T2G level to the upper EG level. Mostly, it is this transition which imparts the color to the complex, since it occurs in the visible or the UV part of the spectrum. But the value of molar extinction coefficient epsilon for these transitions is quite low, since these are Lippert forbidden type of transitions. Hence, the DD transitions, the value of molar extinction coefficient epsilon ranges from 0.5 up to 20 liter per mole per centimeter. But there are cases where the absorption bands in the visible or UV region ranges between the epsilon value of 1000 to 55,000 liter per mole per centimeter. For these cases, such high value of absorption have been suggested due to charge transfer bands which are so much intense, since they are allowed transitions that impart exceptionally deep colors to the respective transition metal complex. Charge transfer transitions are generally much higher in energy in comparison to the normal crystal field transitions, but they impart color if the transitions fall in the visible region of the spectrum. Some of the examples of the complexes which give the charge transfer bands include KMnO4, K2Cr2O7, etc. In charge transfer transitions, either electrons are donated from the low-lying orbitals of the ligand to the metal, or from the orbitals of the metal to the ligand. Both of these transitions are feasible, and in some of the complexes both can coexist.
We will discuss the origin of the charge transfer spectrum. These types of transitions are very intense in nature in comparison to the other transitions such as DD transitions. The reason for their intensity is the fact that they are fully allowed transitions which have very high value of molar extinction coefficient epsilon. The table shown the difference in the value of epsilon for the various transitions possible. From the table, it can be seen that the charge transfer bands are quite profound in comparison to the DD transitions with very large epsilon values. We will discuss the type of charge transfer spectra. The charge transfer transitions can be of two types, namely ligand to metal charge transfer LMCT and metal to ligand charge transfer MLCT. In the case of LMCT transitions, their origin lies in the transfer of electrons from the low-lying molecular orbitals that are principally ligand in disposition to the orbitals that are chiefly metal in nature. Other way round is the case of MLCT transitions. The transfer of electrons occur from the molecular orbitals that are mainly on the metal to the empty pi star orbitals on the ligand, which are comparatively higher in energy in comparison to the metal orbitals. The comparative relationship between the two has been shown in the figure. There are chiefly three types of charge transfer spectrum. First is ligand to metal charge transfer spectrum. Second is metal to ligand charge transfer spectrum. And the third is metal to metal charge transfer spectrum. These type of transitions will be discussed in detail in the first of all we will discuss ligand to metal charge transfer spectrum, abbreviated as LMCT transitions. In this type of transition, the transfer of electrons occurs from the orbitals that are ligand based to the orbitals that are metal based. An example of this type of complex includes chromium 3 plus complex where ammonia is present as the ligand. The LMCT charge transfer spectrum has been shown in figure. Mostly in these cases, the ligands are good sigma or pi donors. Generally, the transitions lead to metal reduction taking place. Thus, metal which is easily reduced combines with the ligand that is easily oxidized, giving rise to a transition low in energy. Therefore, anions that are easily oxidized like iodide often form complexes where charge transfer absorption in the visible region is quite appreciable. The examples include TiI4, which is bright violet, HgI2 red in color, and AgI that is vivid yellow in color. The trend in frequency of absorption of a series of similar complexes can be explained in terms of the ease of oxidation of the ligand. For example, TiCl6 2 has a higher absorption frequency in comparison to TiBr6 2 because bromide ion ligand is readily oxidized in comparison to the chloride ion. Similar trends are observed when the metal cation is strongly oxidizing, where the frequency of absorption follows the oxidizing strength of the metal ion. This has been shown in the figure, which shows that 3D metal ions are comparatively more readily reduced as compared to their respective analogous 4D and 5D metal ions. Because of this, the charge transfer bands of 3D metal ions will be of larger intensity in comparison to that of 4D and 5D metal ions present in the series. Also, more is the oxidation state of the metal ion, more is the tendency of the metal ion to get reduced, and hence large is the intensity of absorption of the respective charge transfer band. Consider a complex with a pi donor ligand. The origin of the LMCT transitions is shown in the figure. In this case, the prospect of excitement of the electrons from the low-lying pi orbitals of the ligands to the T2g or Eg orbital of the metal takes place, giving rise to the charge transfer bands. Nextly, we are going to discuss metal to ligand charge transfer spectrum, abbreviated as MLCT transitions. In these type of transitions, basically the metal orbitals are involved that can easily supply their electrons present in the low-lying molecular orbitals to the empty pi star orbitals of the ligand. Example of complexes showing these type of transitions are carbonyl and bipyridyl containing ligands of the iron, rubidium and tungsten complexes, etc. In all these cases, the pi star empty orbital present on the ligand becomes the receptor of electrons with the introduction of light, and the absorption process takes on. The absorption spectrum of the rubidium bipyridyl 2 plus complex possessing the MLCT transition is shown in figure. In the process of charge relocation, the metal is oxidized and the ligand is reduced. Therefore, for this type of charge transfer phenomena, it is important that the metal oxidation as well as ligand reduction is quite visible. Easily reducible ligands are those which have a low-lying vacant pi-star orbital such as pyridine, which then forms sturdy colored complexes with the metal ions that are easily oxidized such as Fe2+ and Cu+. Depending on the number of electrons in the d orbital of the metal ion, two different transitions are possible: the T2G to pi star and EG to pi star, which both may be observed depending on the conditions. An illustration of the phenomena which shows the transfer of electrons from the molecular orbital primarily present on metal to the unoccupied pi star orbital of the ligand. The third type of transition is metal-to-metal charge transfer spectrum, abbreviated as MMCT transitions. Some compounds possess metal ions in two different oxidation states. In these compounds, a charge transfer transition may occur when the electron moves from one metal ion to the other, with one metal ion acting as the reducing agent and the other acting as the oxidizing agent. Compounds of this nature are generally very intensely colored. An example includes the Persian blue. Next, we are going to discuss the effect of solvent polarity on the charge transfer spectrum. A charge transfer band depicts the transition energy of the transition occurring and depends on the solvating capability of the solvent. In a solvent with high polarity, the shift in the wavelength occurs to the lower value or higher frequency. Polar solvent molecules align their dipole moments maximally or perpendicularly with the ground state or excited state dipoles. If the ground state or excited state is polar, an interaction will occur that will lower the energy of the ground state or excited state by solvation, but if the ground state and the excited state are neutral, a shift in wavelength is not observed, since now polar solvent won't be able to align its dipole with the neutral ground and excited state. Three cases arise when either ground state or excited state or both are polar. The first case is if the excited state is polar but the ground state is neutral, the solvent will only interact with the excited state. This allows alignment of the dipole with the excited state, and thus decrease in the energy by solvation will occur. This will shift the wavelength to higher energy and the lower frequency. In the second case, if the ground state is polar but the excited state is neutral, the polar solvent will align its dipole with the ground state. Highest interaction will take place and hence energy of the ground state will be reduced. If the excited state is neutral, no change in the energy will occur. Since like dissolves like, the polar solvent won't be able to align its dipole with the neutral excited state. Overall energy will increase. It will take place because the ground state is lower in energy. In the third case, if the ground state as well as the excited state both are polar, the polar solvent will align its dipole moment with the ground state. Maximum interaction will occur and the energy of the ground state will be lowered. The dipole moment of the excited state would be perpendicular to the dipole moment of the ground state, since the polar solvent dipole moment is aligned with the ground state. This interaction will raise the energy of the polar excited state.
Summary: DD transitions impart the color to the complex since it occurs in the visible or UV part of the spectrum, but the value of molar extinction coefficient epsilon for these transitions is quite low since these are Lepot forbidden transitions. There are cases where the absorption bands in the visible or UV regions raises between the epsilon values of 1000 to 55,000 liter per mole per centimeter. For these cases, such high value of absorption have been suggested due to charge transfer bands which are so much more intense since they are allowed transitions that impart exceptionally deep colors to the respective transition metal complexes. Charge transfer transitions are generally much higher in energy in comparison to the normal crystal field transitions, but they can only impart color if their value of transition falls in between the visible region of the spectrum. Some of the examples include KMNO4, K2Cr2O7 as well as CrCO6, iridium complex and some of the nickel complexes, etc. The charge transfer transitions can be of two types, namely ligand to metal charge transfer, that is LMCT, and metal to ligand charge transfer transitions, that is MLCT. In case of LMCT transitions, their origin lies in the transfer of the electrons from the low-lying molecular orbital that are principally ligand in disposition to the orbitals that are chiefly metal in nature. Other way round, in the case of MLCT transitions, the transfer of electrons occur from the molecular orbitals that are mainly on the metal to the empty pi star orbitals of the ligand, which are comparatively higher in energy as compared to the metal orbitals. A charge transfer band depicts the transition energy of the transition occurring and depends on the solvating capability of the solvent. In a solvent with high polarity, the shift in the wavelength occurs to the lower value or higher frequency value. Polar solvent molecules align their dipole moments maximally or perpendicularly with the ground state or excited state dipoles. If the ground state or excited state is polar, an interaction will occur that will lower the energy of the ground state or excited state by solvation, but if the ground state and the excited state are neutral, a shift in the wavelength is not observed since now polar solvent won't be able to align its dipole with the neutral, ground and excited state of the molecule.